Okay. So we were just going over Ohm's law, and we're going to do it for R, C, and L, right? And the important thing is to make sure that if the current direction is given a certain direction, the voltage drop across the positive direction, the voltage drop across a passive device, not positive, is plus to negative in that arrow direction. So if I drew it like this, right, the current is in that direction, that's IR. VR would be positive to negative, right? If I did it at an angle, positive to negative. Now, I'm just going to call this out in case anybody has a question, but you should really avoid what I'm about to show you, is that if I have the arrow going this way, but VR going the opposite direction, Ohm's law would be changed to this. So if you mix them up, you're supposed to take it into account, right? But if you're, and I'll leave it at that. I'm not saying this is wrong, but if you do it that way, it's easier to make a mistake. All right. Now, there's something called impedance. All right. And it's in the frequency domain. And we convert like things like DDT derivatives into something called S, which happens to equal J omega. Now, J equals the square root of -1, which many people call I. But since we use that for current so much in electrical engineering, we switch it to J. And this is the frequency in radians per second. All right. Now, the impedance of a capacitor is 1 divided by SC, and the impedance of an inductor is S times L. Once we do, let me finish a thought. Yeah. So once we do this transformation, which we're going to go into later, right? I'm kind of giving you a heads up of where we're going, is that we go from calculus to algebra, sure, complex math, but I'm just going to redraw this down here. So rather than VC equals C, no, I'm sorry. Rather than this, right, we can just set a current IC plus negative VC equals I ZC. And the only thing now is that the current and voltage are sine waves. And I'm sorry, what was your question?
What is impedance, like high impedance and low impedance? What does it mean in general? I forgot.
Okay. Yeah. I was just checking the chat. So, let me change colors here. So, you know, ZC, and so what you do is you take the magnitude, right? Which is basically the real, I'm going to go a little faster than normal because I was going to cover this a little bit later, but you square the real part, add it to the square of the imaginary part, take the square root of it, and you get R, right? If I take the magnitude of ZC, right, the S is J omega, right? But really, it becomes 1 over omega C, and the magnitude here would be omega L. The phase is for later, all right? So with a capacitor, if the frequency is 0, right, DC, 1 over 0 is infinity, you could think of that as high impedance. Or if R is a mega ohm, you could think of that in high impedance. If omega is 0 for an inductor, and let me just make the L bigger here, right? If omega is 0, well, that'd be 0 impedance, right? Now, sometimes people will use high and low impedance, where low impedance, people will just call 50 ohms low impedance. People will call 1 mega ohm high impedance as a shorthand when you're using oscilloscopes and things like that. Did that answer your question?
Yeah.
Okay.
Okay.
Now, the reason why I mentioned impedance so early is that you know, if I add resistors in series, right, R equivalent is like R1 plus R2, right? So here, right, if I put an ohm meter across this, right, all I have to do is that. Well, if I do this for an RLC circuit, Z equivalent is ZR plus ZC plus ZL, right? Which would equal R plus 1 over SC plus SL. And you have to know the frequency in order to actually get a number for it, right? So the thing is whatever we learned way back when about adding resistances in series, it's the same for impedance, okay? It's just, yeah, when we get to the actual impedance of a capacitor and inductor, that can lead to some complex math, right? And I'm just going to double check to make sure I haven't drifted from what I say I want to say. Okay. So there's more than one way to review this. I was going to go over sine waves just now.
Hmm?
Okay.
What? No. Oh, it's carbohydrate.
You didn't stir it.
I stirred already.
Okay. So when we say S, S equals J omega, right? And omega is the frequency in radians per second. Well, of what? Well, it's either a sine or a cosine, a pure sine or a pure cosine or sine, all right? Where there's just one frequency. Now, sure, the period is 1 over f, right? And you can have a square thing with a 1, and this frequency is in hertz. Sorry, I'm getting used to drawing with the tablet again. I can have a triangle wave. Okay. What we're going to find out in this class is that these signals are made up of sine waves that are scaled in frequency and in amplitude and delayed. And then you sum up an infinite number of sine waves and you can get these shapes. All right. So what I thought is, let's just go over some terms. Now, usually this signal will be in volts because it's circuits and systems, but really the units on the signal could be anything. But we're really going to talk about things in time, right? And seconds, right? Now the signal will be A, the amplitude, in this case, sine, right? Omega is the frequency, right? Radians per second. Plus a phase, which I'll talk about in a little bit, which is a delay. Plus some kind of DC term. All right. So let's just, A, the amplitude is that term here, right? But sometimes it's like called V peak, and sometimes it's just shortened to VP. All right. This here is V peak to peak, shortened to V double P. All right. Now, sometimes in the ADLM kit, you tell this it's a sine wave and with amplitude, but then sometimes you're telling it in a peak to peak. Okay. I'm going to draw this up here, right? That's the period, right? And the period equals 1 over the frequency, right? In hertz, right? And frequency is how often per second this thing goes through a cycle, right? But like for instance, when programming in Python, the sine is given in omega, and that if you're going to put in a frequency, right, you have to convert that. So if I were to have a frequency, I'd have A times sine 2 pi right? And then if I substituted 1 over t, I would have that as well. All right. Now, if the frequency equaled 1 radian per second, well, then this would be 2 pi in seconds. This would be pi. We have pi divided by 2. But if we were doing it in degrees, which we often do in circuits, it would be 0, 360, 180, 90, 0, and 270. All right. And then if it was in periods, right, you'd have t divided by 2, 3/4 t, t divided by 4th. So there's all these ways of looking at this. And what happens when you're dealing with impedance and the frequency is a kilohertz, right? Well, you convert that to radians. But once that frequency is assumed, and you calculate your impedance, you don't necessarily care that the period is a millisecond. You want to know where you are on the shape of this curve. Am I at pi divided by 2? Am I at pi? Am I at a quarter period, half period, 3/4 period, right? And now I'm going to tell you something, is that many times, right, they will give you this phase in degrees, right? Even though the units won't match, right? Because 2 pi f, that's radians per second. Then I have to multiply by t. The seconds drop out and I'm in radians. So this part here is in radians, but then this part is in degrees. And you'll see this in textbooks. And the best I can figure out is that you're supposed to know that, which I know isn't necessarily very friendly, but pretty much every document I read will have the phase in degrees, because that's maybe more of a human term, right? Where, yeah, if we're doing science, we're going to use millimeters or kilometers, right? But if we're going on a hike, we talk about it in miles. at least in the United States. All right.
Can I have a
Yeah.
quick question? Are those what are those waveforms next to the sinusoidal waveform here, like on the top right?
So what are these two waveforms here?
Yes.
Okay, so this is just a square wave, and that's like a triangle wave. And I might have said it too quickly, and I apologize. But I was saying that this has a period, and it has a frequency. It's just not a pure sine wave. We're going to find out that these waveforms are going to be made up of an infinite sum of sines and cosines. Okay, it was kind of just telling you these are not pure sine waves. Okay. Did I answer your question?
Yes, you did.
Okay. All right, go back. Now, I might have to turn it on, but if you click on this, the Python code, you can download it and get it. Okay. And something I want to point out is I think when you're learning how to document things in a technical fashion, doing a decent caption, right? This is a sine wave, okay, as a function of time, right? Which you can see, right? But the amplitude is 1 volt, the phase delay is 0 degrees. So see, even I've done it, right? And we have 1 radian per second for frequency, and the DC offset is 0, and the x-axis is in terms of degrees. But this is really just like a scale thing. This is still time, right? Everything here is time. I've just tried to scale it to where you can see the period, you can see everything in terms of pi, right? And so on. Now, you know, we have something called a voltage source, right? Positive and negative. And if it's ideal, right, all right, so from VA to B, whatever I put here, this voltage source can supply whatever current is needed to make that happen. And whatever's here appears from A to B, right? And so sometimes, now, yeah, ideal voltage sources don't really exist because you kind of get this thing of, well, what if I put a 0 ohm wire here, right? Well, there's no resistance, so I can supply infinite current, but infinite current times 0 is not going to give me that voltage, right? And what'll really happen is you'll just blow the fuse, if you're lucky to have a fuse, on your power supply, all right? and a current source, right? You can supply whatever voltage it needs. Oops, there's no positive and negative there. Okay. You can supply voltage to set that current, whatever it is. Now the thing is sometimes the current source, it's, well, what's going on here? How can current flow if there's nothing connected to it, right? Well, it can't. You kind of have to suspend your disbelief with these two elements once you've connected things up, all right? Because if I have a resistance here, right, yeah, that current will flow and a voltage will fall across it. But if that resistance is infinite, well, then I'd need an infinite number of amount of voltage to make it so that I could get that current through the resistor, all right? Okay. So today, it looks like we will get to just to remind ourselves to identify series and parallel circuits. And I'm just going to label that A and I'm going to label that B. And if I want to check, you know, some elements, I just imagine I'm sending some current through. And if it goes through each element with no deviations, right, it's in series, right? But if I can start on one place, right, and take, oops, you know, I can go this way if I'm current, or I can go that way, but I have more than one path to the same point, right? That's parallel, okay? And even though we will go over, and we do use nodal analysis, mesh analysis, things like that, quite often, right, you'd be surprised how often we use voltage division, right? And here's the thing. This could be a capacitor, this could be an inductor, or whatever, and it will have a frequency dependent component to that. But rather than sitting down and trying to do a differential equation or, you know, kind of reinvent the wheel, right? If I have a resistor and a capacitor and I'm using impedance, right? I can just use ZC, ZR plus ZC, V1 algebra to get that to go, right? And for equivalent things, right? You know, R1, R2, right? There's the shorthand. Now, mental note, this only works for 2 elements, right? You can't multiply this by R3 and add R3, right? You have to use the full-blown equation to sum that. But a lot of times in this class, we're going to be using op-amp circuits, and we're going to have impedance, we're going to have RL and C circuits, right, that we don't really need to do nodal analysis on. We just need to use voltage division or something's in parallel, and then we can go from there. Okay, so this will come up quite a bit. Yeah, I know you got to get to 112. So if you got to scoot. If you have a private or a personal question you need to ask me, it's probably better to do office hours or just email me. Probably email is the quickest way to get a hold of me. Okay. But anyway, I'm looking forward to teaching you all, and I hope we have a good semester, and I'll send out those links soon.
Thanks, Professor. You have a good day.
You too.
Thank you, Professor.
I feel like it was a good review.